Hi everybody, welcome to this video. This is our second video about the Fan and Wings project. Right now I'm going to tell you about the system simulations. So as you know, since the project have the BLDC motors which has a complex system inside it. So let's have a close look about it. Here you can see there is two part of it, like one is the electrical side circuits and one is a mechanical side. So system we can divide it in two systems. Let me tell you the working principle of a DC motor first before we get with the simulation, because it's very important to understand this one in order to develop a model, simulating model for this system. First, a DC motor, think like you have a wire, okay, and you give a power supply to the wire, and once there is a power to the wire, there will be a current created in the wire, and once there is a current, there will be a magnet created around the wire, and that wire, if you place it within the permanent magnet, there will be an interaction between two magnets. So that interaction will try to make a force. So think like that wire is your motor rotor or shaft. So once there is an interaction of two magnets, there will be a force. That force will try to spin the shaft, and once it spins the shaft, there will be a rotations. That rotations has a torque. So there is that side is mechanical side, and the electrical that the power that you supply to the system is the electrical side. As you can see from here, this circuit, the power supply is here, V minus plus, and this is the resistance, and this is the inductance. This side is electrical circuit and this side is mechanical circuit. Like this is the coil that the rotor is placed in. So there is also a resistive force here. This J in the formula, we'll use two formula here, which one is Newton second law, and the second one is Kirchhoff law, voltage law. Here, what is Newton's second law? Newton's second law, before we get started with it, let me tell you what are here. Once there is a torque here, there will be a back FEM here created in the circuit here. Newton's second law is, it says sum of forces is equal to mass multiplied by acceleration in a linear system. So this is a rotary system, so think about it like our acceleration is theta double dot here, which is proportional to the moment of inertia J. So J is considered as our mass here. J times the theta double dot, which is acceleration, rotary acceleration. So that is equal to the force applied to the system subtract to the any resistive force. So you can see here the T is the torque, which is supply force, and B is the viscous coefficients. You can see here, which is considered as a resistive. So if you rearrange this equation, you get these values. And Kirchhoff's law says a voltage drop across a closed loop is equal to zero, should be equal to zero. When you try to see this circle inside this circuit, you can see there is a inductance. Inductance is considered here as our mass, but in electrical system, L is considered as our mass here, and here you can understand what is the idea behind here when you apply the voltage, Kirchhoff voltage. So voltage in a circle loop, L times d I over dt, which is theta id, minus R times Re plus the V minus small e, which is equal to our FEM, back FEM. So if you arrange this equation, you get this one again, and this E is proportional to the is proportional to the voltage, the back FEM, which is considered as a resistive voltage, and the torque is proportional to the armature current, as you can see here when there is a torque inside. Yeah, that's it. So we're done for this one today, and next video I will tell you more about the simulation, and we will do the practice of simulating. Thank you.